Hello, my name is Justin Garrigus, and this is a presentation that I gave at the Materials Research Society a few days ago at April 10th, 2025 in Seattle, Washington, United States. The conference didn't allow recording the presentations, so this is just me doing it again, basically. This is a project I did back in the summer of 2024, and we're still working on it. We're just formatting it now. But it's in its final stages, so all the hard work has already been done, basically. So here it is. So this project is called Enhancing Graph Neural Network Prediction of Defect Formation Energies using Transfer Learning on Large Data Sets of Crystal Formation Energies. Okay, so to begin, we have a crystal. A crystal is like this infinite lattice of repeating atoms. And if we were to remove a single atom from that infinite lattice, it would create this thing called a point defect. That point defect can be used for different purposes, like quantum sensors and representing qubits in quantum computers. But you can't just do that out of any old crystal. There's better crystals to do that out of than others. The best crystals to do that out of are crystals with a good defect formation energy, whatever that metric of good may be. So ideally, we would like to do this high throughput material screening where we put in a database of, 100,000 crystals and then have it output a list of 50 that have good values so that we can further screen them, do some more stuff on them. But the problem is that the way we find out this defect formation energy is through doing density functional theory, which is just way, way too slow. It would take several months to calculate a single crystal's value. And as far as I know, that's not something we can speed up either. That's just a human computer effort. We can't just put more money into this problem to make it go faster. So we would really like to improve our speed here so that we can filter these crystals faster. So the way we want to do this just sounds like a deep learning problem now, right? We have the actual method of solving this equation, which we say just takes 4 months to do, and we want an approximation, which is a lot faster. One thing that I also want to note here with deep learning is that after talking with a lot of physicists, it seems like the average perspective of this function is just, a sequence of operations where we put in a crystal and it gives us this defect formation energy, which is true. That is what this function is. A function is just a map of inputs to outputs, right? But if we abstract it a little more by saying, anything that is this map is valid, let's just for this presentation, let's pretend this function is like a human brain. It will make the transfer learning part seem a little bit easier to conceptualize. So we have this human brain which is capable of doing this translation for us. So the prior method of calculating these crystal properties is to use the Crystal Graph Convolutional Neural Network, CGCNN. This has been used a lot in the past already. There's a lot of different projects which have been using this network, and there's nothing here necessarily particular to crystals itself. It's just an embedding layer, graph convolutional layer, a pooling function, and this fully connected layer. This exact 4-layer structure you're going to see that in a lot of different use cases as well. Anything involving processing graphs is just very popular. So that's another thing that's cool about this topic is that this exact deep neural network and the concepts we're just talking about can be used outside of material science. So this CGCNN network is very intuitive. It keeps crystals represented as graphs, where the nodes are atoms and the edges are bonds between the atoms. And it's also fully abstract. That's probably a bad thing for physicists. Physicists don't really like to see things are abstract. They want to keep things concrete, which is why machine learning is a lot more popular than deep learning. In other words, as soon as your crystal passes the embedding layer is just a linear transformation. So you no longer have a crystal. The values in the network no longer represent a crystal at that point. So it's abstract. You can't really explain why you got a result. You just have to trust that it works. Also with the CGCNN thing, it's important to note that for defects, we are basically, for a single crystal, there are multiple atoms in that crystal that we can defect. We can take out one atom and that gives us a defect formation energy, and we could instead defect a different atom in the same crystal and that should give us a different defect formation energy. For this purpose, this crystal graph convolutional neural network did not intend for that when they originally made it. They didn't account for defected crystals. So we can make it work for defected crystals by basically getting all the combinations of defects for a single crystal, averaging those defect formation energies together into a single value, and have that represent the combined defect formation energies for that single crystal. So it's just a single value. That's a little bit of a nuance, but we'll see in the next slide. There are other networks here which are slight variations on this CGCNN model. DGNN on the far left is a model that adjusts CGCNN specifically to work for defected crystals. And the way they change it is by changing that average pool where the vectors for each atom are averaged together. It changes that into this filter pool. So it just selects the vector corresponding to one of the atoms, the atom that we're going to defect. So this just allows us to have different defect formation energies for different inputted crystals, basically. DGNN also adds in new parameters, and that's like the big contribution this model did. Next, align in the middle, that basically just changed the graph This is actually a pretty significant model change. It's a very cool idea, but instead of just encoding the atoms as nodes and the bonds as edges, it also encodes the angles between bonds as another graph. So we have two graphs which are very related to each other. And these two graphs are changed in conjunction. So very cool. It also adds a few new parameters to that as well. And then the final network that we're going to be talking about, there's a lot of different network variants, but these are like the three big ones, is MegNet, which it just changes the embedding layer at the very front and it adds a few new parameters. So it's easy to see here with all these combinations, in order to get more performance out of your model, you can change the architecture, but the big thing is to add in more data. So you have to add in more information to the graph to make it smarter. You have to add in more training examples and all that stuff. And this is the part where I talk about the other research interests that I have, which is outside of material science. This is my way of shoehorning this in. Large language models act pretty similar to this situation. Large language models haven't really changed much since 2017. The architecture itself has stayed the same, but since that point, we've really been changing the model by adding new data, making the model a lot bigger, and adding new training techniques. So the model itself, the model architecture itself, the operations that are being performed is largely pretty much exactly the same. I mean, we've changed the ordering of some operations. We made a few things better, but it's still a transformer. But the big thing that's different is just all the new training techniques we're doing to it to make it just smarter. So let's take a page out of that book, and instead of trying to change CGCNN to be better for this task, let's make the training better. Let's make it smarter. Let's assume that the graph neural network is as capable as it can be from an architecture perspective, and let's make it smarter, basically, just by adding more data. It's important to note that with the defect formation energy dataset, since it takes so much time to calculate that dataset is very small. So we have this constrained learning environment where on the left, let's just pretend those are the data points for the defect formation energies. It's not. It's a lot more. There's a lot more dimensions to it than just one. But as with any like deep learning goal, the goal of deep learning is to take these input points and to draw a line that connects those points, right? And so the smarter your model is, the better it's going to be able to connect those points and still generalize to points that it hasn't seen before. And we can see with these points on the left, since there's so few points in that graph, it's going to be difficult for us to, regardless of how intelligent we are, if we're only given these points, it's going to be difficult to connect them in a smart way. But if you looked at the graph on the right, that sine wave that's going upwards, and if you were to know that this graph is similar to the graph on the left, so that's all the information you're given, you're just saying the graph on the right is similar to the graph on the left, then you can maybe assume that the graph on the left is meant to also be a sine wave. Maybe you can extrapolate like there is something sinusoidal going on about this. So at the very least, you remove the possibility of, a piecewise function. That's really what we're trying to do here. We're trying to just say, here's some related information, and let's have the model draw its own conclusions from that. Another metaphor we can draw here is, let's say that we're trying to teach a child how to play basketball. Basketball is a very hard game for a child to learn just because there's a lot of movement, a lot of fine-grained motor skills going on. It takes a lot of focus and control to do this, and it takes a lot of practice. So instead of just jumping into basketball, one thing you could probably do is to have them play kickball, or not kickball, Foursquare. That's the game above it. Foursquare had a lot of the same actions going on, but it's a lot easier for a child to approach this game. It's a lot less movement involved. So it's just going to be easier for the child to get a hold of that. And then once you learn Foursquare, then you could graduate up to basketball. But before we continue, let's say we didn't have the idea to do Foursquare, but let's say we taught them instead how to play golf before playing basketball. It's certainly not as good of a pre-training task to have them learn to have them learn golf before basketball, because they're so different tasks. But maybe if you're imaginative enough, you can maybe see that a child who knows golf, it might be marginally better than a child who does not know golf going into basketball. There's still fine-grained motor skills going on. You're teaching them patience, right? So we can see they're going to be better off than nothing, which is another interesting thing about transfer learning. Even though we would like to teach this deep learning model a very relevant pre-training task before we teach them the task we're actually trying to learn, it still isn't the worst thing in the world to teach them something that's unrelated, because there's still some information which can be gained from that. This is where transfer learning comes into play, which is what I was mentioning before. If we can teach this model something conceptually similar before we teach them the main thing, then it's going to make it easier for them to learn that main thing. The way we can visualize this on the right, let's say that we have a 2-parameter deep learning model. The white areas represent low-cost sections of the deep learning graph. So we want our model to find the parameters which lead to low costs. That's the whole point of deep learning. So we want the model to find those white areas. It's easy to see that if we were just completely randomized points on this graph, there's a lot of local minima. We can see there's a lot of gray areas, but there's only 2 white areas. So we want the model to find those white areas, and we want a smarter method than just randomizing points. So gradient descent is a bit difficult on this graph, is the whole point. So the way we conceptualize pre-training is, let's say that we had a second graph that is very similar to that graph on the right. And let's say that we trained as much as possible on that second graph. If that second graph is related enough to this graph that we see, then the points in white should be kind of close by each other. So if we're able to find a good solution to the pre-training task, that solution should be pretty close to the solution of this fine-tuning task. That's the whole point of transfer learning. So the more related the task is, the bigger the benefit. And we're just trying to find a good starting point, basically. Now we're back at the defect formation energy. The property that we're going to extend on, instead of defect formation energy, which is a very sparse data environment, defect formation energy only has, let's say, 1,200 training examples, which is very, very small. While pristine formation energy, the formation energy of a crystal with no point defect, that is very, very large. Lots and lots of training examples there. So more than 40,000 in the materials project database. So, and luckily, we can see at the bottom that, on the bottom left, pristine formation energy has this pretty good correlation with defect formation energy. This correlation is not the best metric of success. It is not the best metric of relatedness. There's plenty of situations in which it looks like two variables are not correlated just by doing this linear regression, when really they are very, very related just because of how data is serialized. So you shouldn't take correlation as just the absolute metric for how related two variables are. But in this case, it correlates pretty well, so we can just conceptually think that it's going to be similar. But if you ask a physicist, the way that the physics people on this project described it to me is that the pristine formation energy just shares a lot of the physics with defect formation energy. So if this model were not a deep learning thing, but if it were a human, then teaching them how to find the pristine formation energy should make it easier to find the defect formation energy than someone who does not know the pristine formation energy. Compare that to the pristine band gap, which is another property I'm not very familiar with because I'm not a physicist. I think that's something with energy differences in states. Oh, don't quote me on that. But it's got a slightly worse correlation, but the way it was described to me is just that it has this medium relationship. It's not the best relationship in the world to defect formation energy, but it's not the worst. So we can use that as a good baseline, basically. And luckily at this point, we've done all the groundwork to start this project. We've justified how transfer learning is good. We've found properties that are related. So that's basically all the effort we need to put into it. Now we just put into action. On the right, we can see 3 lines here. The green line with the triangles is the performance of the model over time, as it does not have any pre-training task. So it has this initial jump upwards at around 20 epochs, a little bit less than that, and then it mellows out, goes to the right, and the final performance of that is 0.4851 mean absolute error, which is pretty good. That's good. One thing to note with these deep learning models, people always like to act like we're trying to micro-optimize these models, but 0.4851, that's like, for all intents and purposes, that's pretty good already. So, but let's focus on how we can make that better using this really simple technique. Band gap, the property we talked about, which is pretty similar but not very similar, that one has this big spike at about, that looks like 5 epochs. You can ignore that. That's just all deep learning models. They have to find minimum, so they explore. So that big spike is negligible, but it does have this period between, let's say, 7 epochs and 20 epochs or 25 epochs where it's doing a lot better than from scratch. And that makes sense too, which we'll see this in a few slides more. If we have a property which we pre-train on, which is pretty similar but not extremely similar to the fine-tuning task, then it's going to be at a more stable start position. So it makes sense that it's not going to be as volatile besides that beginning part. It's going to be at a pretty good starting position is the point. But after a while, it's just swirling around the same position as from scratches. So their final performances are pretty much exactly the same. It doesn't really do much benefit after the first 25 epochs or so. Another thing to note that we can relate these facts to large language models, that the fact that at the beginning where it's a lot better than doing from scratch, even though ultimately it's about the same, that has a lot more relevance in data environments which are extremely huge, like trillion data set size elements. Because remember that for like large language models, you're training for an extremely large amount of time. So if you can stop training pretty soon, and that's great, just so you can save the weeks of training and the potentially millions of dollars of GPU time to train. But for our case, this entire thing takes less than a minute to train start to finish, even with pre-training. So it's not as relevant here. So for the thing we actually care about, pre-training with pristine formation energy, the property that has a lot of pre-training data and the property that's most similar to defect formation energy, that does a very, very good job. It stabilizes very quickly. It's very stable, even from the beginning. There's not really any jumps. And it has the best performance here, 0.42 compared to 0.48 for both. So pre-training on the related property is extremely good. With inference, we can see this is just the same data. This is just for the physicists who care about this. The data set that we used has metal vacancies and oxygen vacancies. Metal vacancies are they have a bit more outliers in them. So oxygen vacancies are a bit more stable. So of course, it makes sense that the model is going to perform a little bit worse with metal vacancies just because it's a little more unstable. But the results here are very predictable. Pristine formation energy is just better on both metal and oxygen vacancies, while pre-training on band gap is about the same as pre-training on nothing. And it's just worse with pre-training on the unrelated property. So to summarize this, pre-training unrelated property is just good. Here is another figure showing the relationship between the dataset size and the performance. We can summarize this by just saying, if you look at the figure on the right, they're both displaying the same thing. The figure on the right, we see that the horizontal axis is the size of the fine-tuning dataset. So the size of the number of training elements in the defect formation energy dataset. So in total, there's only about 1,200 elements in that list. So obviously, as we add in more training elements, we should see the performance get better, which is true. So having only 120 training elements is very bad, while having 100%, so 1,200 training elements is very good. So that's a linear relationship. The more data we add, the better our results are. On the vertical axis, we're showing the pre-training percentage size. So we initially have 40,000 pristine formation energy data points. And as we reduce the size, the model gets worse. It's not like the model gets super bad. There's a spike at 30%, which I'll probably talk about that. We'll talk about that in just a second. But generally, it looks like the model is getting worse as we remove data from the pre-training data set. But it still does perform pretty good with even 10% of the data set size. So it implies that the more data we have for pre-training is not all that important, but of course, 100% pre-training data, all 40,000 data elements is still very good. So that 30% jump, we can also see it here. I'll mention it just because it's not very important. We've noticed this jump at 30 and 40% pretty consistently. I think we just need to, it's possible this relates to the outlier thing we were showing here. if the test set contains too many outliers and metal vacancies, then it just makes the results look worse because metal vacancies are harder to predict. We got these results by running 10 training iterations and averaging them together. And so it's possible that the 10 we chose just all happen to contain many metal vacancies. So we'll do something. The DGNN paper did a very rigorous cross-validation method, which was very cool. So we can definitely do something like that. But just to acknowledge the fact that there is a spike there. But regardless, the error ranges here. One thing I mentioned before with pre-training is that it makes the model more stable. So even though band gap has ultimately about the same performance as pre-training from scratch, even though band gap is like that, band gap pre-training on pretty much any property, not every property, but many properties, even if they're just kind of related, they improve the resiliency of the model. If I wanted you to learn basketball and I didn't teach you anything in advance, I just showed you videos of basketball players, then you're going to try out a lot of things to be good at basketball. You're going to be very random in your ability to try out things. You're going to try out some things and then try out completely different things later on, things like that. So your final performance is going to be very random, depending on what things you try out. As opposed to that, even if you learned golf as your pre-training target and then you're going into basketball, at the very least, if you've studied golf well enough, you have a framework for studying. You have a framework to teach yourself how to learn something. So you've probably made yourself more rigorous in your attempts at learning something. So this is a convoluted way of me just saying that pre-training on something makes you more stable in your attempts to learn something, which makes more sense on the left with this parameter graph we saw previously. If we were to pre-train on something, that point that results in on that parameter graph is probably going to be in a stable position. It's going to be on a point that was a maximum, a local minimum on the pre-training target, and that's probably also going to be a local minimum on the post-training target. Even if it's not the global minimum, it's probably also going to be a local minimum or close to one. So that's the important thing here. Very, very cool idea. So that has a lot of implications for different training tasks. If you want more stability, then pre-training on something, it will still probably help. And there it is. Yeah, so that's all we have here for today. So just to summarize the main points, pre-training adds resilience to a deep learning model and it improves performance. So we want to pre-train on something very related to the fine-tuning task. But if we're not able to do something very related, still pre-training on something kind of related is still very good. Another thing to note is that pre-training is just this free improvement. We don't have to change the model architecture at all. All we have to do is just give it more data and have it learn that data and then resume training on the thing we actually care about, the fine-tuning task. So it's free. As long as we have more data to train it off of out of something completely, mostly unrelated, then it could be very good for us. Another few things to point out after the talk, this is usually where I ended the talk, I got a few questions from the crowd about negative transfer learning. At the time, I didn't regard this because for large language models, there's not really, maybe I'm not too familiar. For large language models, we haven't really run into the concept of negative fine-tuning, negative transfer learning, because if you can conceptualize this with like a human, right? If you know any topic in the world, you can link that to any other topic somehow. It doesn't really matter how distinct those two topics are, because it makes sense. You can conceptually link basketball playing to linear algebra somehow. You can link cooking with raising a dog. There's similarities between any two topics. So there's less of a concern of negative transfer learning when it comes to big models, which large language models are. For small models like the ones we showed here, it's like a medium-sized model, but it's still kind of small, especially if we have only 1,200 training elements. Negative fine-tuning becomes more of an issue. In this work, we tried fine-tuning with pristine formation energy, band gap, which are the two we showed here, as well as bulk moduli. In the band gap and bulk moduli, the effects weren't really negative. It was never negative. The worst we experienced was that it just didn't affect performance. But for pristine formation energy, it was just good, very good. So without actually changing the model architecture at all, which is great. So there's that detail about negative transfer learning, just to point it out there. But yeah, so the main point is that transfer learning is good. So thanks for watching this video. You can see my email there if you want to send me an email. Or I guess this is going to be a YouTube video or something, so leave a comment, I guess. Thanks for listening.